Saying we're a little early.
I don't know why it's
We're not that early. It's 11 o'clock. All right.
the only person that's noticed.
Days like today, I have to wrestle the attention of those that are focused on things like open channel flow and Hardy cross method.
No, we did that.
No Hardy Cross.
No, the ordinances are the same. Critical depth.
What's that?
Critical depth.
Critical depth. Reservoirs.
Energy.
Energy.
Step up.
Specific energy.
You don't like general energy?
No.
I've learned some stuff in their class, I'm not even in that class. Apparently, water on other stuff is sticky, but water on water has no stickiness.
Okay. There's an old saying about civil engineering, but really the only two things that you need to know is about factors of safety and that water rolls downhill. So, okay.
You get the gloves?
All right, your degree will be outside the door. No. Yes.
So I'm guessing you're going to tell us that we need to turn our attention and stay in the woods.
That was a good one.
Marshall, get out.
All right, everybody. We are in lecture 31. I think 5.3 is still being graded, but 5.4 is due today. From here on out, the rest of the semester, our focus is beams. We are talking about flexural elements today. So today what I'm going to do is I'm going to take a step back and I'm going to talk about flexural theory. And basically what we're going to do is highlight the important stuff in Engineering 216 that you all forgot, from a year ago. But I'm going to ultimately tell you why basic bending theory isn't enough and doesn't reflect maximum potential capacity of a steel beam. Okay? So what we're going to do is, let me pull up the lecture notes for the slides for today. What I'm going to do is I'm going to take a step back and go back into a little bit of Engineering 216 of mechanics and materials, and I'm going to go back into structural analysis a little bit. Okay? And so the first thing that we're going to do is we're going to talk about just the fundamentals of bending. Okay? So I want to start with this slide. Okay? So what I have here on this slide is a formula. The formula is sigma equals my over I. One of the most fundamental expressions in all of mechanics of materials or mechanics of conformable bodies. And what it does is it tells you what the bending stress is at a particular point in a beam under flexural loading, under bending. Okay? So, in order to compute that bending stress, you need three properties. You need M, Y, and I. So what's M? M is the bending moment. Where does that come from? Well, it comes from the structural analysis that you all learned how to do last semester. It comes from, here's a beam, uniformly distributed load, or whatever loads that you put on the beam, and then from that beam we can draw a shear diagram and draw a moment diagram, and then compute bending stresses from the applied loads on the system. So for example, if I'm looking at this beam, I might be interested in determining bending stresses right there, because that is the location at which the moment is highest, right? Basics of structural analysis. A moment diagram tells us where we need to be worrying about for the purposes of design. I gotta believe that's about the simplest thing that you could understand. Now, the next thing that you need in order to compute bending stresses are some properties of the cross-section, right? The I shape, as it were, has numerical properties that define how it is going to withstand bending stresses and shear stresses, whatever, etc. And the most fundamental property that we need is a moment of inertia. Okay? And in Engineering 216, I taught y'all how to compute a moment of inertia. We're going to go back to that a little bit today. But we need the bending moment, the moment of inertia, and then we need the distance y. The distance y being the distance from the centroid, or from the neutral axis, to wherever it is that we're interested in computing bending stresses. So remember, if you're looking at a flexural element along the bending, or along the neutral axis, we experience no bending stress, no bending strain. It is only as we start navigating away from the neutral axis that we start experiencing either compression or tension. So for an element like this, we're probably interested in finding bending stress at either the top of the beam or the bottom of the beam, because that's where the bending stresses are going to be the highest. And in terms of left to right, where we're interested, probably in the middle, because that's where the maximum moment is. Okay? Does that make sense? Those are the fundamentals of what you learned in mechanics of materials. Okay? Now I'm going to take what we learned in mechanics of materials, and I'm going to introduce some notation and some ideas to you. Some of this we talked about in mechanics of materials, but this is where we kind of really need to start having some review. And so the first thing I want to do is I want to introduce to you the concept of a section modulus. Okay? So the bending stress formula is sigma equals my over I. But I think what we all know is that based on the characteristics of the bending stress profile, the maximum bending stress is either at the top or the bottom. So really, if you're an engineer, you're interested in what's the bending stress either at the top or the bottom. And so what we can do is we can simplify the calculation by, instead of computing sigma equals my over I, we just take sigma equals m over s. And s, or the section modulus, is the difference, or the ratio of the moment of inertia to the extreme fiber distance. In other words, how far it is from the centroid to the very, very tippy top of the beam, or the very, 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 very bottom. And if the section is symmetric, then those distances are going to be the same. With me so far? Okay, now a couple pieces of notation, and I kind of glossed over this on the last slide, but I'll mention it here and then on the next slide as well. So here's our fundamental formula that you all probably remember from 216, but if you notice, I've got these boxes here that, by the way, I'm going to use some notation where it says, I sub x or I sub y. And that stuff we've already seen. So like for a radius of gyration, we have r sub x and r sub y. So these are whether or not we're bending about the strong axis or bending about the weak axis. Same thing with section moduli. We could be bending about the strong axis or bending about the weak axis. What we're primarily going to be focused on in bending is bending about the strong axis, because under flexure, we want to orient the beam where it's going to be most effective. So that's why you see a lot of the slide titles say SX. So I'm just explaining the notation because I don't want you to get marred up in all the details. I want you to get the big picture. Okay? Everybody with me so far? Okay. Now, sigma equals my over I, or sigma equals m over s. Okay? What that does, let me go back to this slide. What that does is it assumes a linear stress profile. So we're in elastic bending theory. Those stresses are linearly proportional to the applied load. Okay? Now, what I can do is I can say, so what does that mean? Let me go back to that a little bit. What does it mean when I say I'm assuming elastic behavior? I'm assuming that the beam essentially behaves like a rubber band. Okay? I take the beam, I apply load, I let the load go, the beam snaps back to its original condition. It returns to its original state. I propose that elastic bending theory holds until the stresses hit Fy. I mean, what does the stress strain curve for steel look like? It's linear, then you hit Fy, and then it starts to plateau. So if I wanted to determine what is the maximum bending moment under which this theory holds true, I would call that the yield moment. And so basically what I'm doing is I'm saying sigma equals m over s, set the sigma equal to Fy, solve for the moment. And I get a yield moment. Okay? Now to be clear, the big thing to keep in mind is the yield moment is the moment at which the extreme fibers reach the yield stress. And what you're going to see here in a little bit is that is not the maximum moment that a beam can withstand. Structural steel shapes, especially ones that are continuously braced, can withstand moments well beyond my, and we're going to see that here in a bit. But the purpose of today is to really sort of bring it back to what we did in 216. So let me give you an example. Let's walk through this. I have a beam here, and by the way, you all aren't going to have to do this one by hand. I have all the calculations in the slides. But let's look at computing the yield moment for this beam. So we're going to compute the moment of inertia. We're going to compute the centroid. We're going to compute the yield moment, the section modulus, all of that. Okay? So I have a beam, and I kept it real simple. Okay? So I have a beam that has two flanges, and instead of using like a W10 by 49 or something like that. I'm actually just using plates so that the math is a little easy. So I have a flange that's 12 inches by 1 inches, a flange that's 12 inches by 1 inches, and I have a web that's 24 inches by 1 inches. So the whole beam is 26 inches tall. A 24-inch web, 2 1-inch thick flanges. Everybody with me on that? So if this beam is 26 inches tall, then the centroid is 13 inches from the bottom. I don't really need to compute a centroid for that. I can just sort of look at it and see. So my extreme fiber distance from the centroid to the very, very tippy top, or the way, very, very bottom, is 13 inches. So if I compute the moment of inertia divided by 13 inches, there's the section modulus. Okay? What I'm going to do is I'm going to compute the moment of inertia, and then I'm going to compute the section modulus and ultimately compute the yield moment. Now, this blue box, I'm going to take some time with this. This beam is symmetric, okay? And so I'm sure that there's folks who will, days in the future will find this dusty video on YouTube and look at this example and go, you are doing this problem way too long. Like you're using it, you could definitely streamline and shorten your calculations because the beam is symmetric. And that's 100% correct. But I'm going to show you a systematic means of computing the moment of inertia for this beam, because you can use that for beams that aren't symmetric. Okay, so we're going to do this problem the long way, but if we do it the long way, I think you'll be more comfortable with the process when you can't use a more abridged version. Okay, so there's a lot here on this slide, but if you had me for 216, you've seen this before. Okay, so the first thing that we're doing here, so I have here the I shape. Okay, so what I'm doing is the first thing I'm going to do, which is this sort of first half of the table, is going to be about computing the location of the centroid. Now everybody in here should be familiar with that from statics, right? If you want to compute the location of the centroid, it's the sum of AY divided by A. Y'all remember that from statics? I'm sure everybody good with that? Okay. If not, don't worry, we'll take our time with it. So the first thing that we do is we compute the area of the cross-section. So what I'm doing is I'm taking the top flange, the web, and the bottom flange, and so for each of these shapes, what I'm doing is I'm saying what's the area. So this is 12 by 1, which is 12, 24 by 1, 24, 12 by 1, which is 12. So 12, 24, 12, the sum of that's 48 square inches. Okay? Now what I'm trying to do is I'm trying to find the centroid. Okay? And so the way that I establish or compute the location of the centroid is the first thing I have to figure out is where am I measuring the centroid from. Okay? So I need a common reference location. I call that a datum in my calculations. So what I did is I placed the datum at the very bottom. Okay? So to walk you through this, let's take the bottom flange, this number right here. How far is it from the very bottom of the section to the center of the bottom flange? Not the whole thing, just the center of the bottom flange. And to get from the very bottom of the cross section to the center of the bottom flange is an inch thick, so we're only talking about a ½ inch from the bottom. Everybody with me on that? Now what about the web? How far is it from the bottom to the center of the web? Well, we go 1 inch and then another 12 inches, so it's 13. What about for the top flange? We go 1 inch, we go a whole 24 inches, and then another ½ inch to the center of the top flange. So you're seeing where these values are coming from right here? Now, in order to compute the location of the centroid, I need the sum of AY divided by the sum of A. So what I'm doing in this column is I'm saying this times this is that, this times this is that, and this times this is that. So 12 times a half is 6, 24 times 13 is 312, etc. Sum all that up and I get 624 square inches. So if I want to, or sorry, that should be cubic inches. That's a typo right there. Woo. I have a mistake. That's a big one. We'll count that as like 0.65 on the mistake time. Again, I'm the one who tracks the mistakes, and it's a corrupt system, I know. All right, so sum of AY over sum of A, we sum that up, we get 13 inches. So what this is telling me is that the centroid of the entire cross-section is 13 inches from the bottom. But we knew that. Like, we didn't need to do that. This is just to make sure that we're comfortable and familiar with the calculations. With me so far? All right, now in order to compute the moment of inertia of the entire cross-section, we have to use the parallel axis theorem. And what the parallel axis theorem states is we need 3 things. The first thing we need is the moment of inertia of each individual shape. Pop quiz, if I have a rectangle, how do I compute the moment of inertia of a rectangle?
Based on side cubed over 12.
BH cubed over 12. That's 100% right. The moment of inertia of a rectangle is BH cubed over 12. So for the bottom flange, 12 times the height cubed over 12, right? So 1, right? Because 12 times 1 cubed over 12 is 1. Same thing for this and this. For the web, it's the base times the height cubed over 12. So it's 24 cubed over 12. 24 cubed over 12 is that. With me so far? So that's the moment of inertia. So in order to compute the moment of inertia, we need the moment of the entire cross section. We need the moment of inertia of each shape, the area of each shape, and we need this little d value. The d is the distance from the centroid of each shape to the centroid of the whole thing. So all we have to do is that minus that, that minus that, that minus that. So some of these are going to come out positive, some of them are going to come out negative. It doesn't matter because you're ultimately squaring the quantities. So I plus AD squared, sum all that up, we get that the moment of inertia of the entire cross section is about 4,900 inches to the fourth. I know those of you that had me for deformables, we did this. Y'all remember that? Okay. And if you haven't, or if you didn't have me for deformables, you had to have done something like this. So, I promise you did. I promise you did. I promise. I promise. All right. All right. Does everybody understand this stuff? Okay. Now, okay. So if I have this beam in question, I have the moment of inertia. I divide by the extreme fiber distance. I get about 377 cubic inches. So if I wanted to compute the yield moment, take this, multiply by 50 KSI, so I get this many inch kips. You all know that moments and inch kips, we like to use foot kips. So take that, divide it by 12, boom. I get the yield moment on this beam is about 1,570 foot kips, okay? Now, what that means is that I go back to a bending stress profile like this, and so look up here. So here's my hand, here's the beam, and as I start applying load, the bending stresses get bigger and bigger and bigger, and once that tip stress, the very tip, reaches Fy, that's the yield moment. And I propose that that happens for this beam when we hit about 5,700 foot kips. Now, that's the yield moment. Is that the moment, the largest moment that the beam can withstand? No. Okay? The reason why is that the yield moment, and this is probably the most important conceptual point in the whole presentation, is that the yield moment is when the tips hit Fy. That's when we hit Fy here and here. But that's when this hits Fy. Can't this part right here still accept load? Can't this still accept load and this still accept load? Yeah, we can keep loading it. And what will happen is that yielding, as we keep applying more and more moment, we will penetrate the cross-section with more yielding until we hit this. And this is when the entire cross-section has reached Fy. So the yield moment is only when the tips of the very top or the very bottom or both have reached Fy. But if the entire cross-section reaches Fy, that is the maximum moment. And what happens at that point is the entire beam has gone past elastic behavior at that cross-section, and we are now into plastic behavior. Okay? And plastic behavior is we start to get those permanent deformations in the beam past that. So what we do is we have a name for that state, and we call that the plastic moment. So to simplify that, to make sure everybody's clear, the yield moment is when we first reach Fy at the extreme fiber. MP is when we reach Fy everywhere in the cross-section. And that, I propose, is the maximum moment that a beam can withstand. Does that make sense? Yes, sir.
So you just, when you're designing, you would just accept the deformation at the extreme fibers?
Yes. Yes, you do. It says, in fact, if you actually look at the plastic zone around where the central section reaches Fy, you get that yielding all the way out. And yes, you do. You didn't expect me to say that, did you?
So like the beams in here, there's been some, if they were designed like this, there's some change that has occurred.
Well, you also have to keep in mind, I mean, we're going to get to factors of safety and expanding what happens here, so we'll get to it. I mean, what I'm saying is that when you actually load a beam to its maximum state, yeah, you get permanent deformations all the way out there. So if we're talking about the beams in the building, and we're going to talk a little bit more about that on Friday, but being able to characterize that is a little bit of a longer discussion, because what we need to do is take each of those elements and ask what are the bracing conditions for those elements. Some of them are continuously braced, some of them are discretely braced. So their behavior is different dependent upon that. So, and you'll see what I mean when we get into the lecture, but the short answer could be that beams might be continuously braced, but girders might be discretely braced. Okay, so here's the thing. So I propose that, I propose to you two things. Number one, I propose to you that the plastic moment is actually the largest moment that we should conceivably assume that a beam can withstand. So that's point one. Point two, and this might be hard to believe, but the plastic moment is actually easier to compute. I argue that if you understand how to compute a moment of inertia, that is way harder than doing a plastic moment, okay? A plastic moment is computed by basically just taking the force in each plate times the moment arm in each plate. How many of you have already had reinforced concrete design? I'm curious. Raise your hand. So if you have already had reinforced concrete design, you have already done a calculation like this. Let's see, the steel rebar in tension reaches ASFY. How about the concrete reaches 0.85 FC prime times the area of the block? So what do? You solve for the depth of A such that compression equals tension, and then you sum moments ASFY d minus A over 2. That's just this. It's no different. It's the same concept. So if you haven't had concrete design, when you get to concrete design, just remember this. So it's the same thing. Okay. So all we do for plastic moments is we just take the force in each plate multiplied by the moment arm. Now here's where things between reinforced concrete design and steel design start to break down, and it actually makes the steel calculation a little bit easier. So in concrete design, you're doing the same thing to determine maximum moment capacity, but in concrete, you're having to deal with two materials. So what you do in concrete is you assume that the steel fully yields, and for the concrete, to keep things simple, you assume that the concrete reaches a stress of 0.85 FC prime, and in order to figure out the capacity, you're having to figure out the depth of the stress in the concrete such that the compression equals tension, and then you sum moments. So you have to look at it from a force equilibrium standpoint. The reason that you have to look at it that way in concrete is because there's two materials. You have concrete and you have steel. We don't have that here because it's just steel and steel. So what we can do is we can say, okay, if the plastic moment is the force in each plate times the moment arm, but there's an Fy common to the whole frickin' thing, we can factor out Fy, and now we have this new term right here. This is a new section property, okay? If S is an elastic section modulus, I propose to you that we now have a new section property Z, which is a plastic section modulus, okay? So if you open up table 1-1 and you look at all of the W shapes, and you look at all of the section properties, remember how we had radii of gyration, and then it also had columns. It had I, it had S, it had Z. That's what they had. One of the other things kind of interesting, if you look at every W shape, you will find that for every W shape, the Z value is bigger than the S value, because steel beams can withstand more bending than their yield moment. They can withstand up to the plastic moment. So Z is always going to be bigger. So how do you compute Z? Z is super easy. Here's what you got to do. You got to find out where the line is such that the area on the top of the beam equals the area on the bottom of the beam. Why do you have to do that? Because this is the axis where all the forces above equal the forces below. If you're bending it like this, these are going to be in compression, these are going to be in tension, and you have to find the line where those two areas are equal, because compression has to equal tension. If compression doesn't equal tension in your beam, then your beam is running away from you, right? So you have to find the place where C equals T. So for steel, it's just find the line where the area above equals the area below. Once you find that, this is all you're doing. You're taking the area times the distance from the neutral axis. Area, distance from the neutral axis. Area, distance from the neutral axis. Area, distance from the neutral axis, right? So what do we have? The area of the top flange, how far it is from the neutral axis. Area of that upper web, how far it is. Area of the lower web, how far it is. Area, how far it is. Take that, multiply it by 50 KSI, boom. That's it. Much easier to compute a plastic moment than it is a yield moment. Much easier. And I'll show you how that works here in a bit. Does that concept make sense? Okay. Now, the thing about, okay, so let me show you something. All right, so the thing about this beam, though, that we kind of have to address, this beam kind of cheated a little bit. This is a symmetric beam, okay? So this beam, there's two things that's true with this beam. This green dashed line is the neutral axis, okay? And that has two meanings. Not only is it where the centroid is, but it also happens to be where the area above that line equals the area below that line. Does that make sense? The reason that those two are in the same place is because the section is symmetric. In other words, if I were to cut this little I-beam out on a sheet of paper and fold it about that line, I'd get the same shape on the top and bottom, right? That is not the case for this beam, right? This beam has a different size flange up here than it does down here, so I'm not going to be able to do that, okay? I propose to you that we have actually two neutral axes that we need to consider, and I propose that they're not in the same place if you have a section that's not symmetric. These are the new terms that I'm going to use with you to try and simplify this. So the first thing I'm going to introduce is what's called the elastic neutral axis. This is what you all thought of as the neutral axis before this lecture started, where the centroid is. I propose to you there's a new centroid, the plastic neutral axis. This is where the area above equals the area below. And they are not in the same place if the section is not symmetric. That might seem deceptive, but you'll see what I mean that isn't the case. Okay? Make sense? Maybe not yet, but let's do an example and see. So I want to look at this section, and I want to figure out where the plastic neutral axis is, and ultimately what I want to do is I want to compute Zx, and I want to compute MP. All right? So, let me pull this up here. I'm going to give you all a second to jot this down, because I really want you all to follow along with this. This is, I argue, one of the easier things that we've done this semester. Does everybody have this or working on it? While you're working on it, I will start to look at our calculations here. So let me redraw this I-beam a bit. Okay, everything's going to be in inches right here. So, and then the web is a 32 by 5/8. Okay? Now, what we need to do is we need to figure out where is the plastic neutral axis. And the plastic neutral axis is the horizontal line that splits this up such as the area above equals the area below. Now, how do we do that? We got to break out some algebra. So I'm just going to assume it's there, okay? Some random place throughout the web, okay? And I'm going to say that that distance is x, okay? Now, if this is x, what is this distance? 32 minus x, okay? Okay? Now, let's see if we can figure out what x is so that that's where the plastic neutral axis is. Now, what is the plastic neutral axis? Okay, the plastic neutral axis is where the area on the top equals the area on the bottom. That's where the plastic neutral axis is. So, let's see if we can evaluate that. What is the area above the plastic neutral axis? Well, it's everything above that line. So it's this plate and it's this, okay? Now, so the area of this is 14 by 3/4. What is the area of this component right here? Okay, but now we got to make sure we're grouping things appropriately. So it's 32 minus x times 5/8, right? So now what we got to do is we got to treat this like it's a algebra problem. So 14 times 3/4 is 10.5, right? And then what we got to do is we got to distribute that. So it's 32 times 5/8. What's 32 times 5/8? 32 times, or divided by 8 is 4, times 5 is 20. Minus 5/8 x. So this is 30.5 minus 5/8 x. Does everybody see what I did there? So 32 times that's 20, 32 times that's that, or sorry, x times that is that, and then adding these up. Does everybody follow along? Okay, so that's the area above. What about the area below? So 18 times 1 1/4, I think that's 22.5 plus 5/8 x, right? So now what I need to do is I need to set those two equal to one another. Okay? And so what I will do is I will add 5/8 x to both sides, right? Because that'll essentially cancel that. And then so that'll get the x's on the right side. To get the numbers on the left side, I'm going to subtract 22.5, right? Because that'll cancel that. So On the left, I'm gonna have 30.5 minus 22.5, that's 8. And that equals 5/8 and 5/8 is 5/4 x. So x is gonna be what? 4/5 of 8, what's 4/5 of 8?
2 over 5.
What's that?
I said 32 over 5.
It's like you don't want to break out your Casio FX 115 ES Plus or similar scientific calculator. Come on now. We're in lecture 31 now.
6.4.
6.4. All right. So, to clarify, so here's this line right here, where this dimension is 6.4. So what's 32 minus 6.4?
25.6.
So this is 14 by 3/4. This is 18 by 1.25, and the web is 5/8 of an inch thick. If you draw a line that is 6.4 inches from that right there, you will discover the point where the area above that line equals the area below. And you can very easily test it by just computing it right now. Now what you're going to see here in a little bit is that is not where the centroid is. The centroid is computed using a different expression. And I know it seems counterintuitive that that should be where the centroid is. It's not, okay? The centroid is referencing the first moment of area, not just the area itself, okay? Now, that is locating the P&A. Okay, if we want to compute ZX, ZX is just the sum of the area times the moment arm. Okay? That's all this is. Okay? So what we have to do is we just have to break this up into a series of simple shapes and just handle it one at a time. Okay. So what I'm going to do is I'm going to break this up into 4 shapes. I've got each of the flanges, and then I've got the web split up into top and bottom. So what we'll do is we'll say the top flange, we'll say the web top, the web bottom, and the bottom flange. So let's start off with the areas, okay? So what's the area of the top flange? That's 14 times 3/4. We already did that. I think that was 10.5. Okay. What's the area of this upper segment right here? What's 25.6 times 5/8?
16.
16. What is 6.4 times 5/8?
4.063.
Is it times 5/8 even? I got 4 even. Is it 4?
I got 4.
Yeah. I think it comes out at exactly 4. What about the bottom flange? What's the area of that?
22.5.
Okay. Did we do a good job in locating the plastic neutral axis? What's the sum of the area on the bottom? 26.5. What's the sum of the area up top? 26.5. So we did a good job locating that. Okay, now let's do these moment arms, okay? How far is it from my dashed line? How far is it from there? So let's do this first one. What is this dimension right here? What's that dimension? The distance from the neutral axis, the plastic neutral axis, to the center of that top flange. 25.975. Do I have a second on that?
Yep.
Okay. What about this part right here? How far is it from this to the center of that rectangle? We're essentially talking about that distance right there.
.8.
Second? What about the bottom? The web bottom portion.
17.85.
Well, okay, so that's the bottom flange.
Oh, sorry about that.
Okay, what about the web portion?
3.2.
3.2. So now the only thing that we have to do is we have to multiply each of these columns. So we have to go this times this, this times this, this times this, this times this. And that gets a little repetitive, so I can do that part for you. This is 204.8, 12.8, 158.0625, and when you sum all that up, you get 648.4. I propose that ZX is 648.4 inches to the third. And I'm going to show you here in a little bit how you would have to handle the moment of inertia. And it is a lot harder than what we just did here. It's a lot harder, okay? But we're not quite done, because if we want to compute the plastic moment, that is just Zx times Fy. Let's see. Did I forget that? Nope, no, I got that. Okay, and what do we get when we chug that part out?
$2,420.
Now that's in inch kips. I don't really like inch kips for moments if I'm trying to explain that. So how do we convert to foot kips? Remind me. Do we multiply by 12? Do we divide by 12? What do we do? Divide by 12, because what we're basically saying, but what is that divided by 12?
$2,701.67.
I propose to you that that is the absolute maximum moment that this beam can carry. Or at least, actually, let me restate that. That is the absolute maximum moment that we should assume that this beam can carry. Okay? Like if we actually went down to the lab, we'd probably get a little bit more for some other reasons, but for the purposes of design, that's it. So now I want to show you, I'm going to break away from this. I kind of want to go back to the slideshow a little bit, but before I do, does anybody have any questions? All right. Now, again, where was the plastic neutral axis? It was 6.4 inches from the top of this bottom flange. That's not where the centroid is, and I can show you. If you take this beam and you do this, you go through and you do what I did earlier where you establish a datum and you go through all the centroid calculations, you actually find that the centroid is in an entirely different spot. From the bottom of the section, it's about 13.4 inches from the bottom of the section. I mean, you can verify the math and see, but that's nowhere near where the plastic neutral axis is. See, what happens is, once you get past yielding, or once you get past the yield moment, because the section is not symmetric, the neutral axis actually has to shift from up here down here in order to maintain equilibrium in the cross section as we go from this to this. If the section is symmetric, that neutral axis stays in the same spot. But if it's not symmetric, then that neutral axis has to move as your yielding progresses throughout the section. So it changes this. But imagine all the work that you have to do to get to a moment of inertia, and then you have to take that moment of inertia and convert it into a section modulus. Now, another thing that gets complicated with non-symmetric cross sections is that your C values are different. So you actually get two different section moduli. You get a section moduli for the top and a section moduli for or section modulus for the top and a section modulus for the bottom. And in order to get the yield moment, you take Fy times the minimum of those two. So all that hullabaloo that you had to do to get the yield moment and then the plastic moment, we just did that and there you go. So what we got just now is we got 6.4, or if you measure it from the bottom, we got 7.65 inches. But the neutral axis, the elastic neutral axis, is about 13.4 inches from the bottom. Okay, does that make sense? All right, I have a couple final points I want to bring up, just some final observations. Okay, so whenever you're dealing with beams that are symmetric about the axis of bending, the elastic neutral axis and plastic neutral axis they always occur at the same location. There's only one section modulus, and MP is always larger than MY. If they're not symmetric, the ENA and the PNA will not be at the same location. You'll end up getting two S values, but it's still, MP is still larger than MY. Okay? Now, here's a final clarification. Do you remember when we were looking at tension members and we would look up angles? And I would say, remember when we were doing like shear lag factors? And I said, remember how there's like sometimes a Y bar and there's a YP? And I said, ignore the YP. Y'all remember that? Now do you know what Y bar and YP are? This is the elastic neutral axis location. This is the plastic neutral axis location. You don't see that on sections that are symmetric, like W shapes, because they're in the same spot. Whenever there is an axis of bending that is not symmetric, you will see both a Y bar and a YP, and that's what they are, okay? Make sense? All right. Any questions? I have probably one of the easier homework assignments I've ever given on this assignment due Friday. You'll see what I mean.
It's very kind of you.
I know you all have a lot of pressure that you're dealing with right now. Good night.
Yeah, but it just keeps flowing.
Again, just channel your positive energy. All right, everybody, that's all I got. I'll see you all on Friday.